Hi everybody, welcome back. Alright, energy conversions. So there's a lot of different units for energy. We're going to focus on two of them. One which is the calorie, which is more of a American and British system. And then the joule, which is the SI unit. So we'll start with the joule. The joule is a Newton meter. So if you notice with this, Newton means force and meter means distance. So the joule is set up as an energy unit related to work. A Newton meter, so kilogram meter per second squared times a meter. Best way to think of a joule is about the amount of energy that you get for burning a candle for 1 second. We represent about a joule of energy. Now, this idea of the calorie is based upon changing the temperature of water. The problem is changing the temperature of water depends upon where the water is. Where there's more air pressure, it takes more energy. So at sea level, it takes more energy to change the temperature of water than it does when you're in Denver, Colorado, where you're 6,000 feet above sea level. So the calorie is not an SI unit, but we're going to define the calorie at sea level and compare it to the joule. So one scientific calorie is the same as 4.184 joules, and you do not have to memorize that. What you do have to memorize is something called the dietary calorie. Now, the dietary calorie on food packaging is actually a kilocalorie. It is 1,000 science calories. So we're going to use capital C-A-L to define the dietary calorie and lowercase c-a-l for the scientific calorie. And of course, 1 kilojoule is equal to 1,000 joules. 1 kilocalorie is equal to 1,000 calories. We expect that you know that already. So that has to be memorized. All right, so doing conversions for it. First of all, let's get you a couple notes and then we'll do the conversions. So we're going to deal with 3 energy units. The first is the SI system, which is the joule. And again, be able to know the relationship between kilojoules, which is what we more commonly find in reactions versus the joule. And the second unit is called the scientific calorie. Which we're going to abbreviate lowercase c-a-l. And again, I would still know the relationship between a kilocalorie and a calorie. And the last one is called the dietary calorie, which is what you see on food packaging. And the dietary calorie is actually a kcal. And so we're going to abbreviate dietary calorie with a capital C to distinguish it from regular calorie. So the conversion problems are pretty easy because you already know the technique. Let's say, for instance, we want to know, we got 5.47 kcals, and I want to know how many calories that is. Again, our technique, start with what they give you, the 5.47 kilocalories, multiply by a fraction, convert back to the base unit. Now that we got the units to cancel out, now we have to put in the numbers. So again, a kilocalorie is bigger than a calorie, so remember that gets to the number 1. And there are 1,000 calories in a kilocalorie. So this is going to be 5,470 calories. All right. What if we want to go from, let's do calories to joules. If we have 48.7 calories, I want to know how many joules that is. So again, start with what they give you. 48.7 calories. Set up a fraction, canceling out calories, and let's convert that to joule. And the numerical equivalent is 1 joule is 4.184 calories. So get out our little calculator. 48.7 divided by 4.184 equals, I get 11.63957,935, so we're looking at 3 sig figs. So I'm going to do 11.6 joules. And then the last example let's say we have something that has 185 dietary calories. I want to know how many joules. All right, so there's a number of ways of doing this. I'm only going to show you one. Let's start out with 185 dietary calories, and let's convert that to science calories. So 1 dietary calorie is equal to 1,000 little science calories. Then we can convert calories to joules. So let's put in the number for that. 1 joule, 4.184 calories. And we get 185 times 1,000 divided by 4.184. And that's going to be 44,216.0619. Again, 3 sig figs, so 44,200 joules. All right, box our little answer. Okay. So in the video guide, it said that I would do specific heat in the next video, but that's going to make that video really long. So I'm going to go ahead and do it now. So let's go back to our notes. We did all this last video. All right, calorimetry. Study of heat transfer using a calorimeter. Now, a calorimeter is a device with an insulator in it, and what we do is we pour water in the calorimeter, and then depending upon how the temperature of the water changes, we can deduce the energy change of whatever we're putting in the calorimeter. Could be a piece of hot metal, or it could be a chemical reaction. When you do the AP class, we'll do heat of reaction that way. But a calorimeter, as best that we can, isolates the system from the surrounding. So they introduced the term specific heat. It's a physical property which is intensive. It's based upon the material that you have, and it's defined as how much energy you need to raise that material 1 degree Celsius. 1 gram of that material 1 degree Celsius. So again, this is intensive. Different materials have different specific heats. Okay, so here's the equation. Q for heat energy equals mass of the object times delta T times specific heat. All right, so let's take some notes here. First of all, the specific heat constant they use as C for specific heat, and it is measured in joules per gram degree C. It can also be measured in joules per mole, but in your textbook we're just dealing with grams of the material. And that's because it's chapter 3, and remember in your book the mole concept doesn't come up until chapter 8. But it could be in joules per mole degree C as well. All right. Q equals M times delta T times C. All right, delta T is like any other delta. It's the final minus the initial. So the final temperature minus the initial temperature. And so they can give you questions like this. They'll give you 3 of the 4 factors and then ask you to solve for one, or they may ask you to just substitute in. So in example 1, let's start with the easiest one. We're going to have, let's do 54.6 grams of water, which has a specific heat value of 4.184 joules per gram degree C. And we are going to raise the temperature from 24.3 degrees C to 71.6 degrees C. They want to know what is the value of the energy that we have to add to do that. Okay, so I'm just going to set up my equation. This is heat energy. So Q is equal to M delta TC. Delta T is T final minus T initial, so I can substitute those values in. 71.6 degrees C minus 24.3 degrees C, which is equal to 47.3 degrees C. So 54.6 grams times 47.3 degrees C times 4.184 joules per gram degrees C. And that value comes out to be 54.6 times 47.3 times 4.184. So I get 10,805.54. So we're going to do 3 sig figs, so 10,800 joules. Of course, a better way of expressing this would be to write 10.8 kilojoules. Okay. All right, suppose they ask us for specific heat. All right, so we're going to take a metal and we're going to weigh our metal in the lab. And let's say, by the way, this is example number 2. And let's say that metal weighs 131.7 grams. And we have calculated through our calorimeter that the value of the energy exchange is, let's do 26,400 joules. And let's say our delta T, we found that the metal changed 61.2 degrees Celsius. All right, so they want to know what is the specific heat of that metal. So again, set up our equation. Q equals M delta T C. And let's solve for specific heat. So Q over M delta T. Now we can substitute in. Our Q is 26,400 joules. Slide that up a little bit. Our delta T, 61.2 degrees C. And our mass, oops, I guess I should have done mass first. Oh well, oopsie poopsie. 31.7 grams. All right, so what is the specific heat of this metal? 26,400 divided by 61.2 divided by 131.7, and I get a value of 3.28. And that's in joules per gram degrees C. Easy, right? All right. Put a whole bunch of these on the test, Mr. Burnett. This is easy. Okay, I will. At least one. Thank you very much. Catch you in the next video where we talk about latent heat and phase change. Until then, have fun.